We were designated Group 1 and tasked with developing a system capable of recording and shaping the impacts experienced by the cart provided to us by our customer. Our design, development, and testing process had to be completed within 4 weeks while still meeting the functional objectives and engineering requirements of the project. Throughout those 4 weeks, the design continuously evolved through testing, failure analysis, and iterative design, as we worked to improve the impact attenuation, repeatability, and overall system performance. The objective of the Pulse Challenge was to transform a basic cart into a functional crash testing platform capable of shaping and recording impact events. The project focused heavily on engineering analysis and data collection rather than simply stopping the cart. Our system was required to measure and generate acceleration versus time, velocity versus time, displacement versus time, and force versus time data. In addition to accurate data collection, the system also needed to satisfy several important engineering objectives: reduce peak impact force, improve repeatability, minimize signal noise, maintain durability, and remain simple enough for repeated operation. The final system also had to fit within 12-inch cube and incorporate found materials into the design. These constraints forced every subsystem to be carefully evaluated through the project. To better understand the problem, we first translated the customer requirements into engineering functions and specifications. Our functional decomposition tree identified several critical tasks: absorb impact energy, stabilize the sensor, guide system motion, and improve repeatability between impacts. We also identified several constraints that strongly affected the design. These included limited available materials, restricted project dimensions, and the requirement to survive the repeated impacts without major structural failure. We then used engineering decision-making tools including objective trees, house of quality analysis, and decision matrices to prioritize our customer needs and compare potential concepts. To better organize the engineering requirements of this project, we developed the House of Quality matrix. This matrix allowed us to directly compare customer objectives against measurable engineering specifications. The primary customer objectives included accurate data collection, repeatability, impact attenuation, structural durability, and ease of operation. These objectives were then related to engineering variables such as dampening coefficient, deformation distance, sampling rate, stiffness, mount stability, and alignment consistency. The House of Quality helped identify which engineering specifications had the greatest influence on overall system performance. For example, mount stability and alignment consistency strongly affected signal and noise repeatability. Similarly, dampening behavior and deformation distance directly influenced impact attenuation and force reduction. The correlation section of the matrix also revealed several engineering trade-offs. Increasing stiffness improved structural consistency, but excessive stiffness also increased peak impact forces. Likewise, dampening improved energy absorption, but could also introduce inconsistent motion if friction became excessive. Using the House of Quality allowed the team to prioritize design decisions using measurable engineering relationships rather than relying entirely on assumptions during development. Once the functional objectives were identified, we began generating multiple possible solutions. The goal during this phase was quantity over quality. We focused on producing as many possible concepts before evaluating which ideas were most effective. 3D modeling played a major role throughout the development of the project. Using CAD software, we were able to design, modify, and evaluate components before physically manufacturing them. This allowed the team to quickly test different structure layouts, rod alignments, and mounting geometries while maintaining the dimensional constraints of the project. The CAD model also helped visualize how subsystems interacted during impact. By creating detailed assemblies, we could identify possible interference points, alignment problems, and weak structure areas before fabrication. Precise dimensions and tolerances were especially important for the sliding rod system and phone mounting assembly, because even a small alignment issue would affect repeatability during test. Once finalized, the CAD models were then used to manufacture several 3D printed components integrated into the final prototype. This significantly improved precision, consistency, and overall structure quality compared to earlier iterations. Tolerances became especially important because the final system relied heavily on friction-based damping. If the clearances between the rods and guide structure were too loose, the system introduced excess vibrations and inconsistent motion during impact. But if the tolerances were too tight, friction forces increased too much and prevented smooth, controlled motion. Because of this, the rod spacing and alignment had to be very carefully adjusted throughout both the CAD development and physical prototyping. Even small dimensional changes affected damping behavior, repeatability, alignment consistency, and overall system performance. Maintaining proper tolerances ultimately allowed the final design to generate more controlled friction forces while still preserving smooth linear motion during impact events. Memory foam bumper. One of the first concepts involved a memory foam bumper. The design relied on foam deformation to increase collision duration and reduce peak impact forces. The advantages of this concept included low weight, simplicity, and easily manufacturable. However, repeated impacts caused inconsistent deformation behavior over time. Suspension pod. We also explored a suspension pod concept designed to isolate the phone and reduce vibration during impact. This concept improved sensor stability but introduced additional complexity and unwanted motion. Crumble cage. Another concept used a crumble zone style structure designed to progressively deform during impact. This concept distributed force effectively but sacrificed durability and repeatability after multiple tests. Electromagnetic damping. We also investigated electromagnetic damping using magnets and copper conductors. The original idea was to use magnetic resistors generated through relative motion between conductive materials and magnetic fields. Although the magnetic effect alone was not strong enough to significantly slow the impact, testing revealed the friction generated between sliding rods and outer structure provided useful damping behavior. This discovery became extremely important during later iterations. Prototype iterations. The initial prototype relied heavily on magnetic dampening concepts combined with guide rod motion. However, early testing revealed several major problems. The system experienced excessive vibration, unstable sensor movement, inconsistent impacts, and insufficient damping performance. Additionally, the phone tray allowed small unwanted movements which introduced spikes in noise to the acceleration data. Iteration 2. To improve stability and repeatability, the design underwent several major changes. The outer rods were connected using reinforced bumper structure, memory foam was added to improve energy absorption, and the phone mounting system was redesigned using elastic restraints and more secure 3D printed tray. These modifications significantly improved alignment, structural rigidity, dampening behavior, and repeatability between tests. Final iteration. By the final iteration, the system had evolved into a lightweight linear actuator style dampening system using controlled friction and foam compression to shape impact behavior. Testing showed significantly more stable and repeatable impact profiles compared to the earlier design. The final prototype combined multiple successful concepts into a single integrated design. Structural frame. The primary structure consisted of lightweight 3D printed parts combined with rod-guided motion systems. This provided controlled linear motion while minimizing unnecessary mass. Damping system. The damping subsystem used friction generated between sliding rods and the outer guide structure. Additional energy absorption was provided through memory foam compression at the front bumper. Together, these systems increased collision duration and reduced peak acceleration forces. Sensor mounting. The phone mounting system was designed to improve sensor stability during testing. Holes were built into the 3D printed phone mount so rubber bands could be threaded through and hold the phone down. Although minor sensor movement still existed during some tests, the mounting system significantly improved data quality compared to earlier iterations. After final fabrication was completed, the system underwent repeated impact testing to evaluate overall performance and validate the design objectives. Each test was analyzed to determine peak acceleration, force behavior, signal consistency, and repeatability between trials. One of the most important performance goals involved maintaining repeatable results across impacts. If large variations appeared between tests, the collected data would become less reliable for engineering analysis. To improve consistency, the cart alignment, phone positioning, and dampening system were all carefully reset before each individual trial. This reduced variability and helped to generate more stable impact behavior. The structural frame was also evaluated after repeated testing to identify any deformation, loosening, or component failure. Because the system experienced repeated impact loading, durability became extremely important during later stages of development. The final design successfully maintained structural integrity while continuing to absorb impact through friction dampening and foam compression. The team also evaluated overall signal clarity and data quality. Earlier tests contained noticeable acceleration spikes caused by vibration and sensor movement. However, later iterations produced cleaner and more consistent data sets due to improvements in mounting stability and system alignment. Overall, the final prototype successfully demonstrated controlled impact attenuation, repeatable crash behavior, and usable engineering data collection within the constraints of the project. Final specifications. The final system specifications included total length of 8 inches, extended rod of 6.6 inches, width of 4 inches, height of 1.5 inches, and a total mass of approximately 403 grams. Data collection and analysis. To collect acceleration data, we used a mobile phone accelerometer application capable of recording time-resolved motion data. The acceleration data became the foundation for all remaining engineering calculations. Acceleration versus time data was recorded directly during impact events. Velocity calculations. Velocity curves were generated through numerical integration of acceleration data over time. Displacement calculations. Displacement was then obtained through integration of the velocity curves. Force calculations. Force data was calculated using Newton's second law, F equals ma. Using the measured acceleration and total system mass, we generated force versus time curves for each test. Repeatability and signal quality. One of the most important project objectives involved repeatability. Repeated impacts are needed to provide similar peak values and consistent signal behavior. Through iterative redesign and improved sensor mounting, later tests demonstrated significantly improved consistency compared to earlier prototypes. Testing results. Final testing focused on evaluating impact attenuation, repeatability, structural durability, and overall data quality. The final design successfully reduced peak acceleration while generating stable acceleration curves suitable for analysis. Repeated impacts produced similar overall signal behavior, demonstrating improved repeatability across trials. The system also survived repeated testing without catastrophic structure. Conclusion. Throughout this project, the design continuously evolved through testing, analysis, and iterative redesign. What began as several rough concepts eventually developed into a functional crash attenuation platform capable of shaping impacts and collecting meaningful engineering data. The final pulse system successfully combined controlled damping, lightweight structural design, repeatable testing behavior, and engineering data collection into a single compact platform. This project demonstrated the importance of engineering iteration, testing, and data-driven design when solving real-world mechanical problems. Thank you.